Okay, so what I want to do today is I want to do a blitzkrieg of chapter 4. If we have a chance to get a little bit into chapter 5, but I don't think we'll quite get that far. We're going to start off with conditional probability. So this is chapter 4, and I think it's section 4.1. 4.1, conditional probability. In some sense, this is the most important thing we can do all course, because almost every probability you have is in some sense conditional on various things going on. Most things are dependent. Anybody ever watch The Price is Right? Okay. Anybody ever see the wheel in the Showcase Showdown? Where whoever's closest to $1 without going over wins. The amounts in increments of 5 cents, you spin the wheel, and then you spin it again. Are those two spins dependent or independent? Dependent. Why are they dependent? I'm sorry? So part of it is the position of the wheel. You don't reset the wheel to the very beginning. It would take up time. That would be less time for them to show products to you and do advertisements. It's boring TV to have them reset the wheel. So when you're looking at things, be very careful to make sure that things are truly independent. How many of you programmed in C? C does not always reset the seed for the random number generator. And so if you're not careful, you could have highly dependent runs. So you've got to be very careful. A lot of things which you feel may be independent are not. Okay, other issues with this is that if you're trying to get $1, you may actually adjust the strength of your spin to try to get it to stop in different places. So what I want to do is I want to talk about conditional probability. So this is the probability of A happening given B happens. And again, whenever you have something in mathematics, it's always good to look at what you are doing. We are trying to find the probability that A happens given that B happens. What must be true about the probability of B? Not 0. Therefore, only consider B such that the probability of B is greater than 0. What is the probability that I will win the lottery given that the Red Sox win the Super Bowl this year? This makes absolutely no sense to discuss. Sadly, we could probably replace Super Bowl with World Series for the Red Sox this year, and it would not make much of a difference. But the Sox technically play baseball. They don't play football. They will not win They will not win the Super Bowl. It makes no sense to talk about the event, A happening given that the Red Sox win the Super Bowl, because that's not going to happen. We just do not discuss this. We just agree we will not discuss this. Okay, so again, it's always thinking, what is the discourse land? All right, so the claim is maybe the probability of A given B is a conditional probability should depend on the following. So can somebody give me some information that the probability of A given B should depend on? Probability of A. Seems reasonable that the probability of A should come into play for this. Anything else that should come into play? Probability of B. The question is, could there be anything else, or is it possible that the conditional probability could only depend on these two things? Now again, what I am going to do now is I am going to do enormous overkill. We do not need what I'm about to do to discuss conditional probability. The reason is most of you are not going to use most of the material I teach you in life. And at least this is now being recorded, so you can never come back to me and say, you told me this would be useful, Professor Miller. Okay? Most of the math you learn, you will not directly use that math. Why are you a math major or a stats major? For the training, for the problem solving, for the ways to formulate things and attack them. That's the useful skill. The specific facts, not so much. So what I want to do now is I want to prove that there must be more. Claim 1 and 2 are not enough. what I'm going to do is I am going to prove there can be no such formula for the conditional probability of A given B using just A and B. So what we want to do is we want to choose very special sets. And this is a great technique to get used to. So choose special A and B. What do you think a good choice for the probability of A should be? There are only 3 good numbers. 1. What's another good number?
0.
What's another good number? Okay, so we'll include probability of B. And there's one other good number in addition to 0 and 1. A half. Those are the 3 best numbers for probabilities. So we're going to look at 2 extreme cases. If the formula only depends on the probability of A and probability of B, let's make them both equal, because we know probability of B can't be 0. Simplest thing we could do is have them both be a half. And now what's nice is, what is the probability of A complement? It's also 1/2. So the probability of A happening is the same as the probability of A not happening. This is one of the reasons why 1/2 is so nice. So case 1, A equals B, and case 2, A complement equals B. So if A equals B, what is the probability A happens given that B happens? 1. So the probability A happens given that B happens is 1. If, however, A complement equals B, what is the probability A happens given that B happens? 0. So this proves we cannot write conditional probability just as a function of the probability of A and probability of B. It has to be richer than that, because these 2 sets have the same probability. Both of these A's have probability of half. Both of these B's have probability of half. But in this case, the answer is 1. In this case, the answer is 0. Therefore, conditional probability is more than a function of the probability of A and the probability of B. So when we're trying to sniff out the formula, our list must be incomplete. So what should we add? What's a good thing to add?
Probability of A and B.
So let's add the probability of A and B. So we're going to add the probability of A intersect B. This is the and. Why is this a good thing to add? Well, we want something that's going to reflect differences in these 2 cases. In this case, A and B is going to be 1. In this case, A and B is just B, which will be 1 or 1/2, depending on how you're looking at things relative. On this side, it will be the empty set. So there'll be very, very different structures here. So adding the intersection of both of them is good. The other thing is, let's go back to the definition of what we're trying to look at. We want the probability of A happen given that B happens. So we want A and B to happen given that B happens. You can hear the word and. And since we're hearing the word and, that suggests we should look at the probability of A and B. So now we want to try to guess what formula might work that involves the probability of A, the probability of B, and the probability of A intersect B. So what would be a good guess? The probability of A given B why would I put a probability of B down below? Yes?
Because you can only restrict yourself to cases where B happens.
Yeah, I'm basically, think of it as I'm restricting my universe of discourse. So maybe originally, here's my entire sample space omega. And then here is B. And now maybe here is A over here. And so only the part of A that lives inside B is going to matter. So I'm looking at probabilities relative to B. What event is going to be the most likely event to happen? What event will have the highest probability of happening given that B happens? Itself, right? The probability the Red Sox win the World Series, given that the Red Sox win the World Series, is 1. So the most likely event is when A equals B, that's got to be a 1. If A is entirely disjoint from B, what should the probability be? 0. So this suggests the probability of A intersect B over the probability of B, that this should be the definition of conditional probability. So this works for A equals B, and it works for A intersect B is empty. And if you look at what A intersect B is physically, A intersect B is the part of A that's also in B. So what we're saying now is, if we restrict ourselves to the case when B happens, we have to adjust the probability of the universe so that now all the probabilities in B. So if before B happened 80% of the time, we're now restricting it so that we're now bumping this up, so it's not like this happens 100% of the time, because I'm telling you B happens. We're rescaling all the probabilities. If I make up half the probability of B, the event should happen half the time. If I make up a third of the probability of B, it should happen a third of the time. So this is a really good definition for conditional probability. The probability that A happens given B is the probability of A intersects B over the probability of B. Whenever you have formulas, it's often good to just rewrite them and see algebraically what goes on. This is the same as the probability of A and B is the probability of A given B times the probability of B. So what's the probability that both happen? It's the probability that A happens given that B happens times the probability that B happens. So this is a nice way of rewriting conditional probability. This leads us to one of the most important notions in the course, the notion of independence. So can somebody just tell me in words, what does it mean for two events to be independent?
The outcome of one event does not affect the other.
The outcome of one event does not affect the other. So in order to make this trip that I took this weekend to Yale tax deductible, Yale was losing, it was not looking good, but late in the fourth quarter I made the bold decision to move my Yale class of '96 hat from my head to my daughter's head. And Yale started doing extremely well. Then we stalled for 2 plays in a row, and I moved the hat from Kayla to Cam. Never looked back. Dependent or independent events? Clearly dependent. So my kids are willing to accept that these are independent events, that who is wearing the hat is not going to affect the outcome of the Yale-Cornell game, though it is fun to pretend that it matters. And it does make the game a little bit more interesting with, my daughter saying, no, keep the hat on, Cam, keep the hat on, Cam. Okay? Independent. Knowledge of one should have no bearing on the other. Is it possible that my yelling makes a difference in the Yale game? Yes, there is home field advantage. If enough people are yelling, this can affect the visiting team when they're trying to hear each other in the huddle. So you have to really think about what kind of effects are there. If you look at how many false starts there are, teams often have more false starts on the road than at home. So you've got to be very careful when events independent. Yes?
Sorry, this might be kind of a strange question, but so far we've phrased independence in 2 similar but slightly different ways. One being the effect of one doesn't have the effect of the other, and the other being our knowledge of one.
Right.
Is there
We have not formally defined independence yet. We're just right now informally talking amongst friends. Hopefully. So we need to have, precisely for this reason, we need to have a mathematical definition of what independence is. This fuzzy feely stuff might work on the other side of root 2, but I shouldn't have said that on tape. But over here, we want something in math speak. Independence. So what about the probability of A given B is the probability of A? Do you like that as a definition of independence? Does this make you happy?
It's not symmetric.
Not symmetric. It's the roles of A and B. It feels like if A and B are independent, A and B should be having the same role. Right? This is giving a special role to B. There's also something implicitly being hidden in this. What's implicitly being hidden in this?
B
B is happening for sure, hides the probability of B is greater than 0. So what about the probability of A and B is the probability of A, probability of B? What about this as a definition of independence? Do we like this? One of the nice things about definitions is you can vote for them. You can choose what you want to define it. Whether or not it's a useful definition, that's another story. Whether or not other people will follow your definition, that's another story. But we can at least say, do we like this definition? What's a positive this has? It's symmetric. What else? Yes?
It implies that first definition that you wrote.
It implies the first definition. In which case?
Because you know that the probability of A and B is also equal to the probability of A given B times the probability of B. So
What do we need for that to be true? If the probability of B is greater than 0 implies the first. If the probability of B is greater than 0 implies above. And similarly, if the probability was A was greater than 0, it would imply something as well. So this is a really good definition. It's symmetric. It does reduce to what we want it to say. The probability that A happens given that B happens is just the probability of A. And we might want to try to fix this and then say, all right, maybe we could fix this. The probability A happens given B is the probability of A, and the probability B happens given A is the probability of B. Maybe we could try to fix it like that. And then that would at least be a symmetric definition. It would be longer, but that definition would still be hiding the fact that we're assuming some events have positive probability. So what this is telling us is that if one of these events doesn't happen, the events are independent. If you think back to, does knowledge of one event happening give you information about the other? Well, if one of the events never happens, and this can become like a semantic discussion, as to what do you do about events that don't happen. It seems reasonable to say that everything is independent from the empty event, from the event that happens with 0 probability. We don't have knowledge of it happening because it never happens. And this is a really nice way of writing the definition. Okay, so now we can come back to our formula for conditional probability. And we had the probability of A intersect B is the probability of A given B, probability of B. Oh, munchkins? So send me an email. All right. So we have the probability of A intersect B is the probability of A given B times the probability of B. Can somebody give me another set that is the same as A intersect B? B intersect A. So these would be equal, and this would be the probability of B given A times the probability of A. So as a consequence, we get the probability of A given B times the probability of B is equal to the probability of B given A times the probability of A. Or we can solve and we can get the probability of A given B is the probability of B given A times the probability of A over the probability of B. And this is called Bayes' theorem. And we will talk more about this shortly today. But it's worth isolating this right now as we've gone into this. The whole idea is you want to calculate probabilities of events. Certain events are easier to calculate than others. And so the idea is we want to take the events we can calculate easily and use those to calculate the events that are harder to calculate. So this is setting up for a situation where it's somehow easy for us to calculate the probability of A and the probability of B and the probability of B given A, but not as easy to calculate the probability of A given B. Right? So it may not be immediately clear that there is such a situation. Okay? But if we were ever in a situation where we could calculate these three probabilities but not that one easily, we could then use those three probabilities to calculate this one. And we will see an example of that very soon. Bayes' theorem is one of the theorems that people have trouble with, I think, more often than not in probability classes. How many of you have been in a statistics class that has really emphasized Bayes' theorem? Okay. The only statistics class I took, sadly, was from the psychology department. And I will talk about that, but not on tape. They did not emphasize anything that was correct, I think. But OK. So what I want to do is I want to try to motivate Bayes' theorem through the expected counts approach. So expected counts. I'm going to start off with a really stupid example. I know it's a really stupid example, but it's a good way to just highlight what's going on. And just to make sure I have the same numbers in the book, I will look over here. So we are going to let, I think, A, so 40% of the time we catch one trout. A trout is a type of fish, not a ball player for the Angels. 25% of the time we catch one bass, another type of fish. And then I think 35% of the time catch nothing. OK? So one of three things happens when we go fishing. We either catch one trout, we catch one bass, or we catch nothing. So let's let A be the event that we catch a trout. And B be the event we catch a fish. Do you think knowing B happens adjusts your probability that A happens? Yes. This is why I like really simple examples, because you can clearly see what's going on. If I want to know what's the probability I catch a trout, if I caught a fish, well, that doesn't happen all the time. Now I start to get really confident. If I don't tell you anything, if I just ask you, what is the probability I caught a fish? What would the answer be? So we know the probability of B is 65%. What is the probability of A? The probability we catch a trout? 40%. So if I don't tell you anything, and I ask, what's the probability I caught a trout today? You'd say it's 40%. But now, as soon as you know I caught a fish, you know this 35% of the time of catching nothing, that's no longer attainable. You've restricted the probability space. And so now, what can you tell me? Is it more or less likely than 40% that I caught a trout? More. Is it more or less likely than 50%? More. More than half the time I'm catching a trout when I caught a fish. So one way to do this is the expected counts is we start off with some number of days. How many days, how many times fishing should we go? What's a good number? 100 would work. 1,000 gives me a little bit more safety. I'll do 1,000 fishing days. All right. How many times do we catch a trout? 400. So 400 times we get a trout. How many times do we get a bass? 250. And how many times do we get nothing? 350. And again, I know we don't need the 0 here. I am setting this up for later today when we're going to infect some of you with tuberculosis. Sorry, I'm supposed to. It will be a little bit easier with the probabilities to just have a couple of zeros and not worry about where should we put things. It's not a bad habit to get into to have a little bit more. So if we now look, these are the days where we catch a fish. So 650 caught something. And then 350, nothing. And so now if I ask you, what's the probability we caught a trout given that we caught a fish, we now restrict our attention to these two boxes. And so now we get the probability of A given B is 400 over 650. So it's 40 over 65. 5 goes into 48 times. 5 goes into this 13 times, if I've done it correctly. And so that would be the probability that we caught a trout given that we caught a fish. Okay? So this is the expected counts approach. I find it's a very nice way to diagram and see what's going on. And if I now tell you we caught a fish, we know exactly where we're restricting to. Okay? We could try to also calculate it using a formula like this. For this problem, do we know the probability of A, the probability we caught a trout? Yes. Do we know probability B, the probability we caught a fish? Yes. Then we have the probability of B given A. So the probability we caught a fish given we caught a trout. Yes. It's 1. This is probably one of the easiest questions I can ask you. Given that you caught a fish, what is the probability you caught a fish? Right? Given that you caught a trout, what's the probability you caught any type of fish? It's 1. So we could also use this formula in this case. We could use Bayes' theorem. We don't have to go through the whole, because the probability of B given A is easy. What about the probability of A given B? That was more work. But these basic events, probability of A, probability of B, these were easy events to calculate. So this is a way to see Bayes' theorem in action. So Bayes tells us it's equal to the probability of B given A, probability of A over probability of B, which is just 1 times the probability of A was 0.4 and the probability of B was 0.65. And that, again, will be the 8/13. Okay? So we could do that using Bayes' theorem. Okay. Any questions on what we've done so far? Everybody's happy with the expected counts? Okay. So what I think I'm going to do is I'm going to skip ahead, and as long as we're here, let's finish off Bayes' theorem, and then let's go back and talk a little bit more about independence. Okay? Anybody considering careers in the medical business? Okay. Email me. I was talking to a recruiter who does have some potential job opportunities. We're going to study today tuberculosis. One of the things that's a little bit annoying is when you take tests for these things, the positive normally means you're infected. Okay? What kind of disease is tuberculosis? Rare or common? Rare, fortunately. Okay? So let's say it infects 1 in 15,000 people. We want to find out if somebody has tuberculosis. Why might you want to know if somebody has tuberculosis? They could die. So it's contagious, right? So if we know somebody has tuberculosis, we can shoot them and just dispose of the body, right? Or if we were more civic-minded, we could quarantine them. Could do a little bit better, maybe. We could hopefully treat them. I'm a little worried about how long it took you guys to actually get to treating these sick people rather than quarantining and shooting them, but all right, so if we know somebody is sick, we can hopefully make them better, or if we don't care about making them better, at least prevent them from making other people sick. So we want to find out who has tuberculosis, so we're going to give tests. So we have a test, and I want to make sure I just get the numbers right. So we have 1% of the time is a false positive. So what that means is you test positive, but you're healthy. So what this means is you do not have tuberculosis, but you are told you have tuberculosis. And then 0.1% of the time, you have a false negative. So you test negative, but you're sick. So again, positive means you have it, negative means you don't have it. Which do you think is worse? Testing positive when you're healthy or testing negative when you're sick? Testing negative when you're sick is typically considered worse, okay? Normally I wouldn't dwell on this, but just based on your civicness, I think it's worthwhile educating you a little bit. All right? If you test negative but you're sick, this is a person who's not getting treatment. If you test positive but you're healthy, okay, you have emotional trauma, that's bad, but that's better than actually being sick and not getting the medicine you need. What do you think we do with people who test positive? Retest, probably with a better test. So the real question is, if you test positive, should you be worried? If you get a positive test, are you worried? How many people are worried at least a little? Yeah, I mean, if I get a test back that says, you know, I'm positive for a bad disease, I should be a little worried. The question is, should I be extremely worried? And that's what we want to calculate. What is the probability we actually have tuberculosis, given that we test positive for tuberculosis? Why do you think we don't just give everybody the really good expensive test in the beginning? It's expensive, right? We don't want to use a very expensive test if there's no need. And then the question becomes, you know, how much is it worth to society to use this test over that test? So we want to calculate. So one possibility is to do the expected counts approach. All right, and so I did this during, I think, Sunday Night Football. So I'm going to say we will have 15 million people. Why do you think I'm starting off with 15 million people? Yes?
Oh, sorry. So you expect 1,000 people to be affected?
Yeah, I would expect about 1,000 people to be infected, and I've got numbers like 1%, 0.1%. I want to keep everything as integers. Can I talk about half of a person? Of course. I'm a mathematician. I'm also Jewish. In the Bible, we talked about chopping off the kid in half. You know, we can do this stuff. But in terms of just examples and having it internalized well, do we really want to be talking about, you know, root 2 of a person or 3/4 of a person? No. Take nice big round numbers, right? So we have 15 million people. How many people are sick? 1,000 people are sick. And how many are healthy? 14,999,000 healthy. Okay? So now we have 1,000 sick people. How many of the people are sick but test negative? So how many will test negative? One. One person. How many will test positive? 999. So if you are sick and you get a positive result, odds are you're sick. Sorry. Yes. No, actually, I think the way I phrased it is even better. If you're sick and you get a positive result, what's the odds that you're sick? 1. So the question is, of course, we often don't know whether or not you're sick. So the question is, if we just know that there's a positive result, are you sick? Well, let's look at what's going on here. We have 14,999,000 people. How many of these people will test negative? Or how many will test positive? Which one is the easier one? All right, so I got 149,990 people will test positive. So we have a 1% false positive. Out of every 100 people who are healthy, one of them will test positive. So I basically just drop a 0. So I get 149,990. Did I drop a 0? Oh, no, it's 100, so I dropped 2 zeros. Sorry. There you go. Now, everybody else is going to test negative. And so that's going to be 14,849,000. I don't think I could have done better in terms of choosing zeros, because this is already just one person here. If I'd done anything smaller, I'd have a fraction of a person.
Should be 14,850,000.
Oh, did I make an algebra mistake?
It should be 0, 1, 0. Yeah, 0, 1, 0.
Oh, 0, 1, 0. Yes, that's right. 0, 1, 0. Thank you. Forgot about those poor 10 people. Okay, so now let's imagine you test positive. How many people test positive? I probably shouldn't be erasing Bayes' theorem right before using Bayes' theorem. All right, so let's say you test positive. So there's going to be 999 who are sick and 14,849,010 people. So that's going to be 150,000. I'm sorry. No. Oh, I'm sorry. I wanted the positive. Yes, I'm sorry. I want the 149,990. And now when I add them together, I get 150,989. So about 150,000 will test positive. How many of them are actually sick? So the probability that you're sick, given you test positive, well, I have 999 who are sick, and I have 150,989. So when you write this in lowest terms, did I bother writing this in lowest terms? No, I just did an approximation. So it's about 0.00661,637. So the probability that you're sick is a little bit less than 1%. Right? 10% would be 0.1, 1% would be 0.01. This is a little bit less. It's about 0.5%. Should you be that concerned if you get a positive result? No. But you should be a little bit concerned, and you should take it again. So why do you think there's such a small probability that you're sick when you test positive? Yes?
Disease is very rare.
The disease is extremely rare. It's so hard to find anybody who has the disease. The problem is we only have 1 out of every 15,000. Well, okay, this is not necessarily a problem, but the good thing is only 1 out of every 15,000 people have the disease. It's very hard. If you look at the chain of people who are sick, almost everybody's healthy. So it's really the false positives that's driving things. And so if you do test positive, you should be a little bit concerned, but I wouldn't be too worried just yet. Wait for that second test. Then you can start to panic. Okay? So this is a huge thing in the medical industry in terms of trying to manage people's expectations. This is often done in terms of trying to keep people on medication. You don't want people getting off medication too soon. In a few years, this could become more useful for you in terms of pregnancy tests, in terms of if the test comes out positive, what is the probability somebody's actually pregnant? All right, we could also do this using Bayes' theorem. So it's the Bayes approach. So we want the probability that you're sick given that you test positive. Well, this is the same as the probability that you test positive given that you're sick times the probability that you're sick, I think, over the probability that you're positive. Yes? So this is coming from the probability of A given B is the probability of B given A times the probability of A over the probability of B. So this is just substituting into Bayes. And so now we just have to calculate these different quantities. What's the probability that you're sick? Do we know that? Yeah. The probability you're sick is what? 1 in 15,000. What about the probability that you test positive? Do we know that immediately, or do we have to work for that? We have to work for that. OK, so we'll hold off on that for now. What about the probability that you test positive given that you're sick? 0.99. So the only thing we're missing is what is the probability we test positive? So to calculate that, what we're going to do is we're going to use what's called a partition. And so we've already used partitions in this course. When we were doing the basketball game, we partitioned Bird winning into a bunch of disjoint events. And then the probability that Bird wins is the probability he wins on 1 shot, plus the probability he wins on 2 shots, plus the probability he wins on 3 shots. So the probability that you test positive is going to be the probability you test positive given that you are sick times the probability you're sick plus the probability you test positive given that you're healthy times the probability that you're healthy. So we've partitioned our space into events. You're either sick or you're healthy. If you want to do this in terms of notation, it's the probability of A intersect B, A given B times the probability of B plus the probability of A given B complement times the probability of B complement. The probability that I test positive given that I'm sick times the probability I'm sick plus the probability I test positive given that I'm healthy given that I'm healthy. Well, the probability of A given B times the probability of B is just the probability of A intersect B. And the next one is the probability of A intersect B complement. And the probability of A intersect B and A intersect B complement, these are disjoint events. In this one, B happens, in this one, B doesn't happen. So what's the union of those two disjoint events? 8. So this is just the probability of A. So to finish the problem, all we have to do is find what's the probability that we are sick. Do we know the probability that we're sick?
Yeah.
Yes, what's this probability? 1 in 15,000. What's the probability we're healthy? 14,999 over 15,000. What's the probability we test positive given that we're sick? 0.99. So 99 out of 100. And what's the probability we test positive given that we're healthy? Another 9 where? Oh, is it 999? OK. Thank you.
Also in the
Oh, and then also one over here. OK. And then what's the probability that we test positive given that we're healthy? I'm sorry? 1%, 0.01. So then this one would just be 1 over 100. We know all these probabilities. So using this formula, we can calculate the probability that we test positive. And then we feed that in, and we get the same answer as expected counts. So same as expected counts. In terms of just starting in the subject, I think the expected counts is the easier way to diagram the problem and see what's going on. But after a while, the more formal way of doing the manipulations is through Bayes' theorem. And basically, as these events happen, this adjusts your probability for other events happening now that you have additional information. And so here, if we want to calculate the probability we're sick given that we test positive, the expected counts approach gives a really nice answer. We can also use the Bayes theorem and have the probability we're sick given that we're positive in terms of these other events. And this is only useful when these other events are easy to calculate. We want to calculate the probability that we're sick given that we test positive. That's what we care about. I'm going to risk asking you a Calc 3 question. Do you remember constrained maxima and minima? You want to maximize the function f given that you have to be on some surface. What method did you use? Lagrange multipliers. At the end of the day, do you care about the value of the Lagrange multiplier? No, it's an extra piece that you use to help get to the answer, but you only care about the final answer at the end of the day. Over here, we have some subsidiary calculations. We don't necessarily care about these calculations by themselves. We care about their combination because that gives us the probability we want. The only one that was really difficult was calculating the probability that we test positive. And we did that by using this idea of partitioning. That if we have a set of disjoint events, the probability that an event happens can be broken up into a union of probabilities. So we will talk a little bit more about that on Wednesday's class. We've got about 4 minutes left, 5 minutes left. And so what I want to do is I want to talk a little bit more about independence. Before I erase this, any question on Bayes' theorem? Yes?
You can use it for more than 2 events.
Yes, you can have more complicated versions. For a first course in probability, I'm going to leave it like this, but there's a split in statisticians between the frequentists and the Bayesians. And I am staying out of that fight. So for that part, I will say that this is a math designated course, not a stats designated course. All right, so we're now all masters of Bayes, and we all know that we should try to cure people rather than killing them. Not bad for a day. Okay, independence. So let's say we want A, B, and C to be independent. What do you think about the probability of A intersect B intersect C is the probability of A, probability of B, probability of C? Do you like this as a definition of independence? Does it have anything good about it? It's symmetric. That's good. Anything else?
It looks like the last one.
Looks like the last, so it seems to generalize. So it generalizes 2 events. But the problem is it only talks about the interactions of all of them. Maybe A, B, and C together are independent, but maybe A and B could be dependent. Or maybe A and B, there could be maybe pairwise things, but not triple things. So the question is, do we need more than just this? Or what about the following? Maybe we want the probability of A intersect B is the probability of A, probability of B. The probability of A intersect C is the probability of A, probability of C. And the probability of B intersect C is the probability of B, probability of C. That if something is, 3 events are going to be independent, they should be pairwise independent. Does that seem like a good definition? It's symmetric. So again, when you start having more and more events, you can start, of course, by playing games. Maybe we could put parentheses around this and consider the event B intersect C one event. And you can use that to try to figure out what the event should be. I want to look at a specific chain of events. So is everybody familiar with what a standard die looks like? Can somebody describe a standard die? Okay, 6 faces. 6 faces. We have the numbers 1, 2, 3, 4, 5, 6. We'll assume all equally likely. So A is you roll an even number on the first roll. B, you roll an even number on the second roll. And C will be you roll a sum that is even for the 2 rolls. Are A and B independent? A and B are independent. What about A and C? Yeah, if A is an even number, is C, the sum is even? It entirely depends on what B is. A provides no information. And similarly, you get B and C are independent. What about all three events? Are they independent? No. If A and B happen, C definitely happens. If A and B don't happen, C doesn't happen. So the triple is not. Okay? So when we talk about independence, we actually need to consider all the different cases. It's not enough to just look at the triple event. We also have to look at all of these cases. So the number of conditions you have grows as you take more and more events. Most of the time, though, you don't have to bother checking them. We will just say the events are independent. Rolling one coin is not going to affect rolling another coin. But when you start talking about sums, that can start having some dependencies. Okay, so I will stop here.